Okay, so good morning, good afternoon, good evening, depending upon where you are. And welcome to the first March webinar of the Accounting Design Project. My name is Cheo Kim, Associate Professor at the University of Oregon. So before we get started, I have a couple of sort of the announcements to make today's presentation smoother. Please mute your voices, but unmute your faces. That means please share your videos. That would be fantastic to Donny if he sees some faces instead of black the screens. And also, if you have any questions, please raise your hands by using the raise hand function or leave a message in a chat box. If I have a couple of questions, I stop Donny and answer those questions. And another one is that unless Donny wants to waive it, let's give him the first 5 uninterrupted minutes so that he talks essence of his papers without being interrupted. That's pretty much all given the interest of time. And let me introduce today's presenter. And we have today Donny Zhao from Emory University, and he's talking about why we focus on distribution instead of points. And Donny, screen is yours.
Okay. Hello, everyone. Thank you for coming to my presentation on this Super Tuesday. So let's have some super discoveries today. So the title of our project is You Have a Point, but a Point is Not Enough. The case for distributional forecasts of earnings. And this is a joint project with Ilya Dijev, Xinyi Huang, she's a PhD student, which will be on the market this year, and Donald Lee, he's our statistician here. So if you ask a lot of very super technical questions, I may have to ask him to help by calling him. Okay, so let me talk about the motivation a little bit. So we know that the earnings is the single most important number about firm performance, and there's a massive literature on earnings forecasting. And typically when people make earnings forecast, they use point estimate. So they will say something like, we expect earnings to be about $2 per share. But ex-ante future earnings is uncertain and is really represented by a probability distribution across all possible outcomes. So in other words, like from today's perspective, future earnings is really a probability space rather than a point estimate. So in this paper, we're trying to derive the distributional forecast of earnings and showcase the utility of this distributional forecast through some examples, through some applications. So in other words, like we're trying to estimate the entire probability distribution of future earnings for every single earning announcement. We're going to estimate the full probability distribution. And then we're going to use the probability distribution to do something which you'll find out soon, okay? So let me summarize the current earnings forecasting approach. So in practice, we have analyst forecast and management forecast. So analyst forecast typically is a point estimate. Like sometimes they might do a range forecast. Management forecast typically is a range forecast. They'll give you a lower bound and upper bound, like probably more than 80% of the time. And then in academic literature, like we have a lot of OLS models that trying to predict earnings or predict change in earnings. And more recently, people start to use machine learning to make forecasts. But here, again, the goal is trying to predict the earnings level or trying to predict the sign of the earnings change. So in this paper, we take a completely different approach. Instead of forecasting any point, we're trying to estimate the entire probability distribution. And we're going to use a machine learning approach that's based on sound statistical theory. And the machine learning approach we use will allow us to estimate the distribution in a very flexible way. Okay, so the main message we're trying to communicate is that point estimates are useful summary statistics, but they are insufficient for the entire distribution. By considering the entire distribution of earnings, people are able to unlock more information and are able to make better forecasting and the investment decisions based on that. Okay, so let me explain a little bit why future earnings is a probability distribution. So we know that future earnings is uncertain, right? To see this, consider that earnings is a function of X and epsilon. So X here represents observable variables, such as accounting numbers. Okay, they are observable to researchers, observable to anyone who make a forecast. Epsilon represent unobservable variables, and it could include inside information or like future events, such as pandemic or like wars that affect firms' earnings. Okay, so let me use a simple example to explain why then future earnings is a distribution. So assuming that the functional form here, G, is a linear function, okay? It's a linear function, so G is X times beta plus epsilon, so linear relation. We have seen this probably too often. Epsilon here is a normal distribution with mean 0 and variance sigma square, okay? So in this case, clearly future earnings is a normal distribution with mean X times beta and variance sigma square, okay? So the uncertainty about future earnings is completely characterized by this probability distribution, by this normal distribution, okay? So in a general case, if we do not assume a linear functional form for G, and we do not assume a normal distribution for epsilon, then uncertainty is fully characterized by this distribution, this probability distribution here. Okay, it's a very general probability distribution. Okay, and later on we are going to see that when we estimate this probability function, we also do not make much assumptions. It's a non-parametric approach. Okay, so in practice, this probability function is what we want to estimate. Okay, what we want to get. We know that in practice we don't observe it, so we have to estimate. Right, we have to estimate the probability function. So a typical approach to estimate the probability function is to make some assumptions about the underlying distribution. You can assume that, oh, the distribution is a normal distribution or log normal distribution, Bernoulli distribution. Like you make assumptions about the distribution, and then you're trying to estimate the parameters of the distribution, okay? But we think this approach is very restrictive and probably unrealistic for earnings, right? Because we know that earnings distributions are like ill-behaved. They have like heavy tails, skewed, things like that, okay? So we are going to use a machine learning approach called a box head. It's a recent development in the distributional machine learning based on like very sound statistical theory, and it allowed us to estimate this probability function in a non-parametric way. Okay, so let me tell you a little bit about how box estimate the probability function at a very high level. Because if you want to go to the details, I think it will take like a whole day. So basically, Boxhead will try to estimate this S function, which is basically 1 minus CDF, cumulative distribution function, okay? Then how they estimate this X function here? They try to estimate the lambda here using a non-parametric approach. It's a non-parametric maximum likelihood estimation. So it's very similar to OS in the maximum likelihood framework. So basically, when you estimate OS using maximum likelihood estimation, you assume there's a normal distribution, and then you're trying to fit parameters. Here, on the box head, you just do not assume normal distribution. You let the machine learn from the data and tell you what's the distribution. So box head is trying to estimate the lambda here in a non-parametric way. Basically, it's like a tree-based machine learning approach, okay? So in our setting, the Y variable here, that's the earnings here, which is earning per share divided by stock price at the beginning of the quarter. So it's like you run a regression of earnings on a bunch of variables. And the variables we use are like accounting variables, typical accounting variables. Okay, so let me give you some examples of the distribution, like the outcome of our distributional forecasts. So this is
Donny, we have two questions. Do you want to answer them?
sure.
Okay, let's Tong, you go first, and then Ayang, you as a second.
Thank you, Zhao. So Donny, I have a question regarding the scalar, the stock price. Would you go?
Here.
Yeah, I agree. I understand you need a scalar. However, you may use something like accounting variable, like net operating assets or total assets, so forth. Because I'm a little bit has some reservation introducing the market price into your, because you are trying to investigate the properties of earnings, right? So if we introduce an external variable, this may disturb the interpretation of the results. You understand my concern, right?
Oh, I totally understand your concern, but I think that would be a big problem if the price here is Q, simultaneous. Like the price is simultaneous with the earnings. Then we're trying to estimate. Then when you predict this EPS divided by P, you don't know whether you predict EPS or you predict the price. But in this case, the price is deterministic in a sense that the price is determined a long time ago. So you are not forecasting price here in this exercise.
You are saying it's lagged, right? It's a lag.
Yeah, it's lagged. So we are not forecasting price at all. The price is fixed before you make the forecasting decision.
But still, your estimation of distribution is it's ex-ante distribution as well, right? You understand what I'm saying, right?
Yes, it's ex-ante distribution. Absolutely correct.
Yeah, so okay, but have you tried robustness, for example, like the things I suggested,
I see.
divided by total assets or something to that effect, or net operating assets, right?
Yeah, that's a good point. We probably can try to do that as well. Like basically, then we'll be kind of we'll be forecasting like ROA instead of this earnings divided by market value of equity. Yeah, that's a good point.
Okay.
We have not tried that, but worth trying. I guess there's another question, right?
Hello, Donny. So when I read the paper, I think you first defined earnings this way as EPS divided by the beginning of the quarter stock price per share. But a lot of examples or implications you actually draw is about whether the firm is going to meet or beat analysts for their own EPS, which is the numerator here. So I just want to know what's your motivation for scaling it, because my understanding is if it's a within firm estimate, it's not cross-firm comparison, why do you need a scalar here?
Oh, good question. So I have to clarify something. So when we use the machine learning approach to estimate the distribution, we run like a panel regression, basically. That's why we have to standardize it. And then because the P here is a lag one, that means mathematically you can rescale it back for each firm.
Okay, thank you. I missed that. I thought that
I did not mention that in here.
Yeah, because you require 10 years of the quarterly data. I thought it's a within firm estimate. Okay.
Yeah, it's not within firm, it's a pool regression. So one thing about machine learning is that if you want it to perform well, you need a very big training sample. You need the training sample to be very big. And because we are trying to estimate the distribution here instead of point estimate, that means the demand for bigger data is even greater. So that's why we have to like use panel data, and we will use like past 10 years or 5 years to make sure it's accurate.
Thank you.
Yeah. Okay, so just some examples of the distribution output. So there are 9 companies here. We are trying to forecast the earnings in a quarter in Q3 of 2021. So the Apple, Amazon, Boeing, so many companies, you can tell that they are all single peak, so makes sense. And the shape can be different across firms. And then here, trying to show you Apple's distribution over time. So this is all Apple's data. It's from year 2019 to 2020. Okay, so there are 8 quarters here. And you can see that over time, the distribution can change quite a bit. Okay. So now let me talk about the data and sample a little bit. I already mentioned this. So our test period is between 2011 and 2021. But for each year in the test period, we use the past 10 years panel data to train the model. And then once we have the model, we apply the parameters in the test period to the model and get a distribution. Okay, so different firms will have different distribution because they have different X. Okay, so we also apply like some filters to the data. So if the stock price very small, we get rid of it, and we want the earning announcement dates in IBORs and CompuStat to be very close to each other because we have a abnormal return around earning announcement test. Okay. Okay, so the final sample include 283,000 firm quarter observations between 2001 and 2021. So they include both the test periods and the training period. Okay, so some summary statistics.
Donny, we have 2 more questions.
Okay. Sure.
Kenneth, why don't you go first, and then Ayang again, you're the second.
Just a question here for clarification. When you estimate the model here, do you iteratively update the model? So you use the past 10 years.
Yeah.
And that window changes over time. So does that imply that your test here is constricted to firms that are survival firms for 10 years?
No, not necessarily.
Not all the firms are necessary to survive for 10 years in your sample. Or
sorry. Okay.
My question
can I answer
was
now? So sorry, I guess the voice a little bit like come out.
Yes,
out, so.
Yeah.
So basically, we do not require the firm to survive for 10 years. When we use the past 10 years, we use the past 10 years in the population. So which means a firm might just join CRISP or CompuStat, but we still use the firms in the past 10 years to estimate the model and then apply the models to the new firm's data.
Okay, I get it. Thanks.
No problem. There another question?
Yes. Hi, Donny. So I want to go back to slide 8 and 9 because like after you introduce this new statistical tool, I kind of want to make sense of what the estimated distribution looks like. So I think for page 8 here, if you see CHB, which is Chevron, has much wider dispersion in your estimate compared to other firms. Do you know what drives a firm to have a bigger kind of dispersion around the mean compared to all the rest, like Coca-Cola or Apple has kind of thinner estimate? Like, have you diagnosed the difference in dispersion across firm in your results?
Good question. That's something we have not done yet. So basically, let's say you can potentially use our distribution to measure uncertainty. And then you can study like what determines each firm's uncertainty after you have this measure. That's something we have not done yet. And that's something that future research could do as well, but we could also do that. depending on the feedback along the way. Yeah.
Yeah,
we
because
have
I
done
think
but
that
that's a
the
good
other
exercise.
the other question I have is that on page 9 is like is a time series for Apple, but if you look at the x-axis, you see that Apple's fiscal year end is September 30th, right? And then for closest to September 30th or December, the EPS is estimated around 0.5 to 1, but for other quarters, it's actually between 3 or 4, 4 and 5. So it seems like it's a huge shift in the mean estimate from quarter to quarter. So that's the other thing is how stable this prediction is, right? Even it's within firm against the rest of the firms traded in all 3 stock exchanges. It seems the mean estimate shift very quickly from one quarter to the other. So
yeah,
I think a little bit of validation test or explanation about what what's the estimates coming out of this black box will help us understand the strength of this tool and weakness before we compare it with human estimates from the firm or from the Wall Street.
Yeah. That's a good point. Just let me clarify something. So currently, the x-axis, they are not standardized in certain way. So I would say you cannot directly compare 2 graphs because sometimes they are not in the same scale. So it might look bigger, but actually if you put it in the same scale, they might not look bigger. So I think you raise a very good point. We probably want to standardize the x-axis. Then you compare like apple to apple. You can see, oh, the scale here is the same across all the figures. And then you see how the shape change. Currently, because we kind of want to zoom in or zoom out, that will change the scale. So I would say that the figure here might not super intuitive yet. We need to improve on this, absolutely. And you're also correct that we definitely have to validate our distribution, and that's what we're going to do next. And hopefully you can give us some feedback on that too, like whether we did a satisfactory job in validating our distribution. Yeah, we're going to devote much effort on validating our distribution. Let me go there right away. Okay, so we have to validate our distribution.
Donny, we have 2 questions from the chat box. And Sudipta, did Donny answer your questions, or you want to ask a question? And then Jeremiah after Sudipta.
I'm sorry,
My question is just a variant of the question that Ayung asked. This is about the y-axis rather than the x-axis, but it's the same question.
Okay, gotcha. So Jeremiah?
Yeah, mine is just, I sort of have the advantage of Elia's coming to present this Friday, so I've been reading the paper. You don't cite a couple of papers that already claim to be forecasting the distribution of earnings. And so I think it's worth citing those and discussing how yours is different from that.
Yeah, we're aware that there are some papers talking about the distributional forecasts, which is not surprising because like this distributional forecast idea is very standard in statistics. So this idea of distributional forecast has been like floating through the literature, accounting literature. And our paper is the first to like formally estimate the entire probability distribution of earnings using a approach that's based on sound statistical theory. And our machine learning approach will allow us to estimate the distribution in a very flexible way. And then we'll show how we can use the distribution to do something that we think is pretty cool. So you are right. We probably should talk more about this, like differentiate further. Yeah.
Well, my point is you don't cite those papers and they claim to do the same thing. So, you know, when you discuss it, you know, like why is yours, the big difference between yours and those papers, I think, that maybe you're claiming is that you get some sort of continuous distribution forecast. They get a bunch of points in the distribution. And so explaining or showing why your approach is better than those other approaches, I think would be, you know, important.
Yeah, absolutely. Your point is well taken. So we are going to address that in our new draft. Absolutely. Yeah. Thanks for the comment.
Ken, do you have
Yeah,
any questions or no?
No,
Okay.
I had the same question. I mean, this is something that has been done a number of times
Okay.
before. And of course, we are interested in, you have to evaluate it vis-a-vis others to see that this machine learning approach is superior. That would be of interest.
Yeah. No, your point is well taken. We'll probably do that in the future. Absolutely. Any other questions?
Not yet at this point.
Okay.
Keep going.
Okay. Validation. Okay, so we are going to use two approaches from statistics to evaluate the quality of our distributional forecast. And the first approach is called a probability plot. It's for entire distribution. So let me explain this plot a little bit. The x-axis is the predicted probabilities based on our estimated distribution. And the y-axis are the actual probabilities based on the real data. So if our estimation of the distribution is correct, then you are going to see that predict probabilities are very close to the actual probabilities. In other words, you are going to see like a lot of dots that will occur in the 45-degree line. Right? If you see a dot in a 45-degree line, that means the predicted probabilities based on our estimated distribution is very close to the actual probabilities. So let me just elaborate a little bit further. Okay, so let's say this is our estimated distribution. Okay, for an earning announcement. Okay, and let's say we estimate, then we get the 10th percentile value based on this estimation, okay, which is y here, okay? So if our estimation is correct, that means 10% of the time, the actual earnings will be less or equal to this 10th percentile value, okay? Then we go to the data and calculate how many times the actual earnings is actually less than or equal to y. And we do this at a 5th percentile, 10th percentile, until the 95th percentile, okay? And then we can see that almost all the percentiles, the predicted probabilities are very close to the actual probabilities, meaning that our entire distribution is very close to the actual distribution.
Donny, we have one more question from Ayang.
Yep.
Are those like in sample actual probabilities or out of sample?
Oh, out of sample.
One more question from Jeremiah.
Yep.
Just because I don't understand this very well, are you testing against the entire realized outcome of earnings? Because I guess I don't understand, because you're estimating firm specific distributions, right? And
yes.
You can't observe a firm specific distributional outcome.
Mm-hmm.
I mean, you just see one point of what happened with the firm, right?
Right.
So are you testing against the sort of aggregate distribution, and so you don't know if the individual firm level distribution is correct, or is it somehow testing the individual firm level distribution?
Is testing the individual firm distribution, but we can do that by using all the firms in the population. So this distribution we estimate for every single firm, right? Every single firm will have this distribution, and every single firm will also have a Y. So different firms, they have different distributions. That means they have different Y. Okay, this Y is the 10th percentile. That means on average, if our distribution is correct, 10% of the time, the actual earnings will be less than or equal to Y. We cannot observe that for each individual firm, but we can observe for the population. So if our distribution is correct, then in the population, we're going to see 10% of the time, the actual earnings will be less than or equal to their corresponding Y. Different firm will have a different Y. You just count how many times in the population that the actual earnings is less than this estimated 10th percentile based on our distribution.
Yeah, thanks. That's helpful.
Yeah. Okay, then we use another approach called CRPS, CRISP, very similar to CRISP. It's called a continuous ranked probability score. It's a very popular approach used to evaluate the quality of a distributional forecast. So let me just explain a little bit. If a forecast is a point estimate, then typically in order to evaluate the accuracy, you compare the point estimate with the actual data, actual point, and you calculate like mean square error, okay? In our case, we're trying to evaluate a distributional forecast. So we have to compare the CDF with the actual data of the CDF, okay? So in this graph, the red line here, that's our estimated CDF, okay? Our estimated CDF. And the blue line here represents the CDF of the actual data. So it's a piecewise function because actual data is a data point. It's not like a continuous distribution. So it's a piecewise function, okay? The probability just jump at an actual value, okay? So we want the two CDF to be close to each other. And if they are very close, that means the error here, the red error here will be very small. That means the CRPS score will be very small. I'm trying to give a high level picture, like a big picture here. So I use some words that's a little bit loose here. But basically the idea is that we want to see that the error here to be very small. That means the estimated CDF is very close to the actual CDF, okay? And we calculate this CRPS value for 3 types of forecasts. And the first type of forecast is the mean based on OS regressions. So instead of running machine learning fancy approach, we just estimate an OS model, which is the mean by construction, okay? We calculate the CRPS value for this mean. Then we also calculate the CRPS for the mean of the distribution that we estimate. So in this second point, instead of using the entire distribution, we use the mean of the distribution, okay? So 1 and 2, both are point estimates. They give you a mean from different approach. One is from OS, one from machine learning, okay? And 3 is what we do in this paper, the entire distribution based on box head approach, okay? And we're going to see how the forecast accuracy change from 1 to 2 and then to 3. And our prediction is that the forecast accuracy metric, which CRPS, will improve, decrease from 1 to 3. And let me tell you the table. So column 1, that's the CRPS value from the OS regression mean. So that's our baseline here for each year. We can just focus on the last row here, which is summary measure for all the years, okay? So we can see that from 1 to 2, so basically moving from OLS mean to machine learning mean, the accuracy improved by 18%. From the OS mean to the entire distribution based on machine learning, the improvement is 36%. So the improvement in forecasting accuracy is quite big, even from the mean of the machine learning approach. Okay, so
Donny,
yeah.
we have a question from Ken.
Yeah, just a short question here. If you were doing it with OLS, and you were using the full distribution, estimating the full distribution in OLS, what results would you get then? Have you tried that? Because now you have a very kind of naive type of OLS. So what if you did something more sophisticated with OLS?
Oh,
Do you
so
see my point?
Yeah, I see your point. When you estimate OLS, you also have a distribution, which is normal distribution, right, by construction. So we are saying we can use that normal distribution and then compare with our estimated distribution and then see like what are the differences. I see. Yeah, we have not done that. That's a good point. Yeah. Any other questions? Saw some chats.
No, at this point.
Okay.
Yep.
Okay, so after we validate our distributional forecast, now we're trying to showcase the utility of our distributional forecast through some examples. So one thing we argue that people can use our distributional forecast to create a prediction range. Okay, and even better, people can attach a degree of certainty to the prediction range or prediction interval. So for example, you can say, oh, earnings per share will be between $1.70 and $2.30 with 80% chance. Okay, so you can create any prediction intervals you want based on your decision context. Okay, and you can create a prediction range based on any level of coverage probability. Okay, so it could be 80%. You want the actual earnings to fall into the range with 80% chance or 95% chance or 20% chance, like any number you want. And this probability plot, same as before, it is used to validate the accuracy of our prediction range here. So before it was a point in the previous probability plot. This is for the prediction interval. Okay, we show that our prediction interval is also quite accurate by comparing to the real data. Okay, here comes something interesting. We can use our distributional forecast to evaluate management forecast and analyst forecast. Let me focus on management forecast. So we can calculate the probability of coverage by management forecast. You know that the management forecast typically is a range. So there's a lower bound and there's a upper bound for the management forecast. And we can calculate the probability that this range will cover actual earnings that will be announced later. So every time when managers give you a range, we can calculate how likely or what's the probability that the actual earnings will fall into this range. And that's something we call coverage probability. And in order to calculate this probability, it's very simple because we have the probability function now, right? So you just plug in the lower bound, plug in the upper bound, and then subtract the probability when you plug in the lower bound. And that's the coverage probability implied by the management forecast. So let me give you some example and some specific example, delta. I will give you the full sample results later, but let me give you an example here. So delta. So delta has a management forecast back in 2018 Q1. So the management forecast at that time was between 0.65 and 0.75. When we calculate this coverage probability, we find out that the range here, the management forecast range here, has 28% chance of covering the actual probability. So it's a little bit low. If you want to have a high probability of covering the actual earnings, then lower bound and upper bound has to be like stretched further out. Okay. And now we're trying to calculate the median. Now we're trying to give you some summary statistics of the coverage probability for the entire sample. And we find out that on average, this coverage probability is very low, like only 30% if you look at the median of the coverage probability. So that means like on average, when managers give you a range forecast, it's only going to cover the actual earnings by 30% of the time, which seems to be low. And then here comes the question, then, is it strategic or is it a miscalibration? Okay, in this case, we have some evidence based on the literature. So Andy Core, so he had a paper at a JE conference last year. So it's a survey paper. They ask managers, and one question is about the management forecast. So basically ask managers, when you give a range forecast, what's the likelihood that your range will cover actual earnings? And on average, managers believe that their management forecast range will cover earnings about 78% of the time. Okay, but when you do the calculation, the coverage is actually 30%. Okay, so this seems like it's a miscalibration. And like for future research, people can use our approach to identify like miscalibration in management forecast. And like you can study what the determinants of the miscalibration and what the consequence of this miscalibration. So it could be useful for future research. And I think can be useful for managers too. So managers right now, I don't know how they'll react when they look at our paper. So basically, we have a tool that can help them to correct those potential miscalibration, right? So they can look at our distributional forecast and say, oh, maybe my forecast is too narrow. Let me rethink about our forecast. So here we're not trying to say that, hey, managers, please take the number literally from our distributional forecast, because we understand that managers might have different information set. Okay, so their forecast can be different from ours. But at least our forecast, distributional forecast, can help managers to make a better forecast. So it could be useful to managers too. Okay.
Donny, we have two questions, and Ayang, this time you go first, and then Kenneth, you are the second.
Hi, Donny. I think this question, my question is a little broader. I want to kind of see what's the implication of your study, right? And then I can see that it helps researchers like us to have a benchmark to right now study what analysts and managers forecast team behavior, right? Is another benchmark compared to all those different prior studies. But what would you say to Coca-Cola's executive, given that you give them this tool? How do they communicate with other investors, human investors, about their next quarter's earnings? Because it's unlikely they are going to give very detailed probability plus range estimate, right? It kind of runs into the information overload, right? If I want to ask ChatGPT about whether it's going to rain tomorrow, of course, it can give me the whole distribution, but at some point, I cannot really digest and use that information. So what would you say to a Fortune 500 executives, like how do they use your tool to actually improve their communication with the investment community?
So I think like managers, when they make a forecast, they probably have some statistic in their mind, and they probably will not want to tell you all the statistics in their mind. So for example, here, according to Andy Core's paper, they believe that when they give the range forecast, it's supposed to cover the actual earnings about 80% of the time, right? So maybe they don't have to tell you what's the coverage probability when they give you the forecast, but they can at least, when they give the forecast, at least they can try to aim at 80% coverage. They can give a wider range, and in their mind, they know, okay, this is going to be about 80%. And exposed, it is actually 80%. You don't want to give a range that you think is 80% coverage probability, but exposed only 30%. That seems like a major miscalibration, in my opinion. Yep.
Kenneth?
Questions?
Kenneth, you can ask a question, and then Derek after Kenneth.
Yeah, I mean, what you get here is some kind of confidence interval for where the outcome will be. That is conditioned on all the kind of indicator variables that you have. So in a sense, it is what you would predict that here is where the earnings would be, given all the public information that is available and that has been massaged in this kind of prediction model in a very nice and effective way. But isn't the point of the management forecast to be able to say something more? They are supposed to have inside information about what's going to happen. So isn't the point for them to be able to give a very narrow interval? So I don't think they would be very enthusiastic about these wide intervals between $0.25 and $5.3. That would signal that they don't know what they are doing.
It could be, I guess, like this finding might be consistent with the literature that say managers are a little bit over confident. Some evidence in the literature. So managers on average are like overconfident. Yeah, I'm curious about how they'll respond to our findings. I don't know, so I don't want to speculate too much.
Just the one thing, Derek, that Sudipta, is your question related to Kent's question?
Not quite. It's related to this 30% and 78% and all of that. The actual benchmark should be how often the actual earnings falls in the forecast range that managers have given. Then you can tell us whether that actual probability distribution is 30% or 60% or whatever, right? It maybe it's 80% fallen, in which case 78% is accurate. But until you use the actual data, I don't understand.
Oh, I see. Yeah. Sorry, I did not present the information yet. Ex post, it was 30%. Right? You can actually calculate the number, and it was 30%, which is very close to our estimate. So that's kind of another evidence suggesting that our distributional forecast is quite accurate. Even though, as Kent mentioned earlier, that managers might have some inside information, so their distribution could be different from us. But somehow when we use our distributional forecast, the ex post, the coverage probability is 30%, very close to the actual ex post coverage probability, which we think is quite interesting.
Derek, it's your turn.
Thanks, Jay Wu. Thanks, Donny. Really interesting paper. So Sudipta's question was very similar to my question. I was going to ask if you've looked at the actual range of that. And then just one other sort of clarification question. And sorry if I missed it, but what's the timing look like for the data that you're using to estimate the distribution and then the timing of the management's forecast? Like, are you trying to align those? So example, like if you're using data from last quarter to estimate distributions, are you only using forecasts for managers that happen before the end of last quarter?
Oh, I see your point. Yeah, ideally, managers and our management forecast and our distributional forecast should be made at the same time, ideally. But currently, we did not do that. So our distributional forecast is made like right before earning announcement. Same time as the last analyst forecast. Not a management forecast, but I think you're right. Like ideally, you want the two forecasts to be made at the same time. Yeah, that's good.
Yeah, I guess, and then just if that's the case, I'm just curious what you think. So to me, it seems like the model that you've built has a slight advantage over managers in that realm because it has information that's available after the date that managers made their forecast. Now, I still haven't thought through sort of the ex post comparison you made, and I don't know if that's a problem. If ex post you're still finding that managers' errors, it's only covering 30% of the time, which is what your model predicts. I don't know, but some, and I don't know if it's in the paper, but some discussion of that might be helpful.
Yeah, no, your point is well taken. Yeah, I have to think more about it. Like, how does that affect the results? If we make the forecast using more advanced info, like more recent information, then our forecast should be tighter.
Yeah, so it almost seems like it would be opposite of like what you're finding, like even stranger that management's forecasts are tight relative to even your distribution. So I don't know, at least seems worth discussing.
Yeah, no, that's a good point. We'll think more about that. Yeah. Okay, any other questions?
Donny, we have one more question from Steve.
Sure,
Hey,
absolutely.
Donny, I think Derek, this is sort of almost a follow-up on the spirit of Derek's point. Given that several people have said that there's many reasons not to offer this sort of a forecast strategy by managers, the thing that's surprising me is you're not talking more about the possibility of using this in an algorithmic trading strategy and being better at predicting forecast error.
Oh, interesting. So can you tell me a little bit more? So for forecasting management forecast errors.
Yeah, I just thinking that if you're coming up with a better prediction of the distribution that actual earnings are going to fall relative to forecast, which is an analogy to your whole point or an allegory to your whole point, then given that the information is not being given by management and there's reasons for them not to do so, the people I would think find your model interesting are algorithmic traders to trade on the possibility that they can better predict the actual outcome of the earnings relative to forecast or the forecast error.
Now that's a good point. We did not do exactly what you said, but we did something very close to what you said. So the next application, so because of the time constraint, I'm going to jump a little bit. So making money in the stock market using our distributional forecast.
I meant to say, Donny, up front, I haven't had a chance to read the papers, but I was just surprised. I was surprised it hadn't entered the discussion yet, but now it is.
Yeah, no problem at all. So since we have the distributional forecast, we can use our distribution to estimate the probability of beating analyst forecast or missing analyst forecast by m cents. So here we create a measure that reflects the differential probability of beating analyst forecast by m cents relative to the probability of missing the expectation by m cents. And then we're trying to form portfolios, hedge portfolios based on this measure. Like take a long and short position, and then we're trying to calculate abnormal returns around the earning announcement, like 3 days around earning announcement. And we do find abnormal returns around earning announcement, 61 basis point, 3 days centered on earning announcement date. So let's send in.
Donny, Jeremiah has a question related to making money.
Oh.
Go ahead, Jeremiah.
So since there was the trading strategy idea, that sounds a lot like what the Eric So paper did. So I wonder if you tested compared to that paper too, right? Because his paper says if you can anticipate forecast errors ahead of time, therefore you can sort of capitalize on that. To me, that seems like that would be the benchmark that you should compare against, right?
I see. Yeah, I read the paper before. It's a while ago. I probably need to take a closer look at the paper and see how to incorporate that. Yep, thanks. Okay.
Donny, you have approximately 5 minutes to go.
Yeah, so I'm going to jump a little bit. So we have the abnormal returns here. Next, we're trying to do some tests and see whether the abnormal returns are driven by our measure's ability to predict earnings surprise. And we use two analyses to show that we can make abnormal returns in the stock market, and that's because our differential probability based on distribution can actually predict earnings surprise. Okay, using two analyses, and then we're also trying to show that the differential probability measure we use, they actually convey information more than what's conveyed by the mean of the distribution. So our probability measure does not just capture the mean, it captures more than the mean, okay? So now I have to say something that Ion suggests me to say. Okay, so any thoughts on accounting design issues? So we know that many numbers on the financial statements are accounting estimates, right? For example, like bad debt expense, that's an estimate of future bad debt. Okay, so currently those estimates are represented as a single point in the financial statements. That might lead people to believe, especially unsophisticated financial statement users, to believe that these numbers are certain. Managers know the numbers for certain, but it's not the case, right? So we suggest that managers might want to consider providing some distributional forecast in the annual report. Okay, this might help users understand that there's uncertainty associated with those estimates, and the distributional forecast can also give investors some way to quantify the uncertainty associated with each estimate and help the users make better forecasting and investment decisions. And this kind of a distributional forecast has been done like to some extent in practice, right? So for example, like when some firms disclose estimates, they will do some sensitivity analysis. They will say, oh, in this scenario, the estimate will be this. In another scenario, the estimate will be this. So it's already like some forms of distributional forecast, but we recommend that maybe managers can do more of it to help people understand the nature of the estimates better. Okay.
Donny, we have a question from Benjamin. I know that you're running out of time, but Benjamin, you can ask a question. Yeah.
I'll try.
Yes, hi, Donny.
Hey, Ben.
Quick one. So in terms of when these returns are realized, do you see that they're concentrating around the earnings announcement, exactly the time when you would expect the surprise to be realized?
Hello? Oh.
Did you get the question or not?
Donny, you are, yeah, you're
Sorry, I
unmuted.
got
Yeah.
cut by Zoom somehow, like it threw me out, and then I'm sorry for the technical issues. Yeah, Ben, go ahead, please say that again.
Do you see that the returns are concentrated around the earnings announcement window? Because I would expect that the surprise is realized in that time frame.
Do you see what?
The abnormal returns, are they mostly realized during the earnings announcement window?
Yes, in our stock trading example, we only look at abnormal returns 3 days around earning announcement.
Sorry, I did not see the paper. Cool.
Yep.
Thanks.
Okay, so let me conclude. And if you guys want to stay and talk with me, you're welcome. So most extend earnings forecasts are point estimate. So in this paper, we're trying to use a machine learning approach to forecast the entire probability distribution of future earnings and right before earning announcement. And we show that our distributional forecasts are quite accurate. And then we're trying to use our distribution to evaluate the management forecast and analyst forecast. And we show that the management forecasts are like miscalibrated. And we should suggest that managers can use our distributional forecast to like correct or identify some miscalibration. Investors can use our tool too to potentially identify those miscalibration. Same for researchers. We also show that we can use the information implied by our distribution to make some money in the stock market. So thank you so much for coming to my presentation on this Super Tuesday. I hope you have some super discoveries. Please you're welcome to stay and talk with me if you have any questions. Thank you.
All right, thank Donny for a great presentation, and thank all of the participants for, you see there are a lot of clapping hands here. So thank you for active participation today. And as Donny mentioned, you can stay in this Zoom if you have additional questions with Donny. And the one last announcement is that we will have another fantastic presentation in 2 weeks, March 19th, So I hope to see you guys again in 2 weeks. And otherwise, have a great day, great night, and see you later.